Hello and welcome to all. Today lecture topic is transmission line. In this topic you will study the concept of transmission line, primary and secondary parameter for analysis of transmission line, derivation and numerical. Yes, so first we discuss what is transmission line. Suppose when you want to transfer the power from one end to the another end at low frequency, then we have to require a single wire. But what happens when we want to transfer the power at microwave frequency? Then this function or this process is fulfilled by the transmission line. So what is the transmission line? Any physical structure that will guide an electromagnetic wave place to place is called a transmission line. Okay, so I think you are able to differentiate what happened in case of the transmission line. So the transmission line is used at the microwave frequency for transfer the power from one end to the another end, but at the low frequency this will be happen through the single wire only. Yes, so next we will move which type of parameter or which type of circuitry is required for analysis of the transmission line or the wire, or we can say analysis of differences between the low and the high frequency. It means that at the low frequency the element that is used for analyzing a circuitry, these are called the lumped circuit or the lumped parameter. Lumped parameter, it means we have to calculate the value of the element, for example resistor, inductor, capacitor physically, but at the microwave frequency such treatment of the circuit element is not possible. So the parameter that is used for analyzing the circuitry at high frequency, that parameters are called the distributed parameter. What happened in this case of the distributed parameter? We just consider what we have to written here, consider to be a lump, but it is not actually a lumped parameter. Here we just say consider to be a lump. So this consider to be a lump, these are the distributed parameters. So for analyzing any transmission line, the distributed parameter are used, but for the electronic circuitry or the electrical circuitry the lumped parameter is used. Okay, so in this case what happened, basically at the microwave frequency we just focus on the wavelength. So the formula for the wavelength is what? This is the lambda equals to c by f. So this is because the dimension of the circuits are comparable to the wavelength of the wave according to the formula is this. Okay. Yes, so next, how to define the transmission line? A transmission line is a two-port network connecting a generator circuit at the sending end to a load at the receiving end. So whenever we compare the analysis of the transmission line with the circuit theory, then what happened? Unlike in circuit theory, the length of a transmission line is of utmost importance in transmission line analysis, whereas the length of the transmission is not necessary for the electric or the electronic circuitry. But in case of the transmission line, of course, the main consideration is depend on the length. What is the length of the transmission line? Different types of so there are different types of transmission line. Some common type of transmission line are shown here. This is a coaxial transmission line, two-wire transmission line, parallel plate transmission line. Next one is a microstrip transmission line, and this one is the waveguide. So in this course or in this slides, we mainly focus on the coaxial and two-wire transmission line. Yes, so next we will move towards the behavior of the transmission line. For understanding the behavior of the transmission line, here we just assume the distributed parameter are used for this transmission line. So to study the behavior of transmission line, a transmission line can be considered to be made up of number of identical symmetrical T section, just like as Z1 by 2, Z1 by 2, and this one is the Z2 that is shown in this figure. If the last section is terminated with its characteristic impedance, the input impedance at the first section, if it is terminated at the characteristic impedance, then its input impedance is Z0. So each section is terminated by the input impedance of the following section. So what happened, as you all know, what is the characteristic impedance of the T network? The formula for the characteristic impedance for the T section is that will be equivalent to Z1 Z2 with the multiplication of 1 plus Z1 by 4 Z2. Suppose these type of n section are considered, then what happen if n number of T section are cascaded, and if the sending and receiving current are Is and IR respectively, then what happened? The Is is what? This is the source current, that will be equivalent to IR is multiplied by e to the power n multiplied with the propagation constant, where gamma is the propagation constant. So what is this n? N is the total number of n section that is connected in the form of T circuit. So where gamma is the propagation constant, and what is the gamma? Gamma is equivalent to the alpha plus j beta. So actually what I am saying to here we have to use the distributed parameter for analyzing the transmission line. In next slide we will show how is it possible. Yes, so here what happened for the transmission line, since each conductor of transmission line has a certain length and the diameter, it must have a resistance and the inductance. Actually what happened in a transmission line, physically there is a no resistance and inductance, conductance and the capacitor, but what we have to assume, there are a distributed parameter. Distributed parameter, it means there is a two wire filled with the air. It means it behave like as in a capacitor, because what happened in case of the capacitor? Capacitor is nothing, just a two parallel plate filled with some dielectric material, and whenever the electric current is passes through this inductor, then whenever the electric current is passes through this wire, then it behave like as in a magnetic field. So due to this, the inductive behavior is happen inside this transmission line, and just because of distortion, some part of the current is restricted. So due to this, it behave like as in resistance. So these parameters are distributed inside this transmission line, but physically there is a no resistance, inductor and the capacitor. So so these parameters that we have to consider for the transmission line, these are resistor, inductance, capacitance and conductance, but they are calculated or defined as a per meter or the per length, and these are called the primary constraint or the primary parameter for the transmission line. Now in continuation with primary parameter for the transmission line, we have to define what is the resistor. So resistor is what is defined as a loop resistance per unit length, that having the unit of ohm per kilometer per length. It may be in a kilometer, it may be in a mile, it may be in an inch, that depend on the transmission line. Okay, here we not consider simple resistance, just have the unit is ohm only, but the parameter that will be calculated or defined for the transmission line is defined in terms of ohm per length. It may be in a kilometer. Inductance is what? Inductance L is defined as the loop inductance per unit length of the transmission line, and it is measured in Henry per kilometer. Similarly for the capacitance with the unit of farad per kilometer, and same for the conductance that having the unit of mho per kilometer. Now we summarize the primary parameter for the transmission line as, since we use the following distributed parameter to characterize the circuit property of a transmission line. So R is what? That is the resistance per unit length. L is the inductance per unit length. G is the conductance per unit length. And C is the capacitance per unit length. And what is this del Z? This is the increment of length. So these parameters are related to the physical property of the material filling this space between the two wires. So that is all about the primary parameter of the transmission line. Yes, next one is the secondary parameter. Secondary parameter for the transmission line. Why it is called the secondary parameter? These are called the secondary parameter because these parameters are derived from the primary parameters. So what are the secondary parameter for the transmission line? These are the propagation constant that is defined by the gamma and the characteristic impedance Z0. These are called the secondary parameter of the transmission line. Since what we know that the propagation constant is what? This is equivalent to the alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. So whenever we have to write down the gamma in terms of the R, L, C and G, that is in terms of the primary parameters. So what are the formulas for that? Then what happened? The gamma is what? This is equivalent to the root of Z is multiplied by Y. Z is the total series impedance and Y is what? This is the total shunt admittance. Okay, so R is what? This is equivalent to R plus J omega L, and Y is what? That is G plus J omega C. And how to define the characteristic impedance? The characteristic impedance is the ratio of root of Z over Y, and you just put the value of the Z and Y in this equation from here. Yes, so the next calculation for alpha and beta in terms of the primary parameter. Since we know that the gamma equals to alpha plus j beta, and we also know gamma is equivalent to the Z into Y, the whole power of 1 by 2. Then Z is what? This is equivalent to the R plus J omega L, and what is the Y? That is replaced by the G plus J omega C, as we have already seen in the previous slide, right? So the alpha gamma is what? This is the alpha plus J beta or the I beta. You just put this value. Now we have to solve this equation and find out the value of the alpha and beta in terms of the primary parameter. What are these? These are the R, L, G and C. Yes, so this is the equations, or this is the process for calculating the alpha and beta. Now finally we calculate the value of the beta. So the beta is what? This is equivalent to root of omega square LC minus of RG plus under root of Rg minus omega square Lc of whole square plus omega square in bracket Lg plus Rc bracket close square divided by 2. And similarly we have to calculate the value of the alpha. So this is the phase constant and this one is the attenuation constant. Now next calculation for the perfect transmission line. Remember one thing, the perfect transmission line and the distortion-less line is totally different. We will discuss in my next lecture what is the condition for the distortion-less line. So here you have to remember there is a difference between perfect transmission line and the distortionless line. Perfect transmission line, it means the ideal transmission line. So whenever we have to consider the ideal transmission line, so what are the conditions for the ideal transmission line or the perfect transmission line? R should be equivalent to 0 and G should be equivalent to 0. So whenever you have to put these two value in the previous equation, then the attenuation constant becomes 0. It totally becomes 0, because in a perfect transmission line there is a no attenuation, but of course the value of the beta is exists, that's the phase constant is exists. So whenever we have to put these two condition in a previous equation, then the beta is what? This is equivalent to, beta square is equivalent to omega square LC, that is calculated from the equation 1.32. And what's the value of the beta? That is equivalent to omega root of LC. This value of beta is calculated for the condition of the perfect transmission line. So now we calculate this beta, then we calculate the next value, that is called the velocity. So what is the velocity? The velocity is equivalent to lambda into f. So whenever we have to multiply this equation by 2 pi, multiply and divide this equation by the 2 pi and the 2 pi, so that this velocity is equivalent to omega over beta. So beta is what? This is equivalent to, since from the above equation what is the value of the beta? Beta is equivalent to omega root of LC. Then from this equation, since we know V is what? That is the omega by beta, then what happened? Just put the value of the beta here from this equation. The beta is what? This is the omega root omega under root of root LC. So you just put the value of the beta here. Then what's the value of the V? That will be equivalent to 1 divided by root LC. It means here we have to calculate the velocity in terms of the primary parameter. Similarly, here we have to calculate the beta in terms of the omega and the primary parameter for the perfect transmission line. Okay, I think you have got it this point. And whenever you want to calculate the wavelength, so the formula for calculating the wavelength is what? That is the 2 pi by beta. So what is the wavelength? The distance traveled by the wave along the line while the phase angle is changing through 2 pi radian is called the wavelength. So after the calculation of primary and secondary parameter, now students, you are able to calculate or able to solve the numerical. So first we have to discuss this problem. A coaxial transmission line used to transmit substantial amount of power at frequency of 100 megahertz has the, so this is what? This is the operating frequency, has the following distributed circuit coefficient at that frequency. These are, R is given 0.098 ohm per meter. So here you just remember this thing, here not the R is not given in simply ohm form, this is given in the ohm per meter form. Similarly for the inductor, and similarly for the conductance, and similar for the capacitance. So what you have to find out in this numerical, these are the characteristic impedance of the line at the frequency of operation. So whenever you want to calculate the characteristic impedance, first of all we have to know the formula for that. So the characteristic impedance is what? This is equivalent to root of Z over Y. And what is the formula for this Z? Z is what? This is equivalent to R plus J omega L. And what is this Y? This is equivalent to G plus J omega C. Write this thing. Yes, so for this given value we have to put in this equation, and finally we are able to calculate the characteristic impedance. seen here. This, what is the r value is 0.098, so this is the value of 0.098. and what's the next is j omega l. So here is a j omega is replaced by the 2 pi f, so this is the 2 pi, and what's the value of the f? This is 100 megahertz. So mega, it means 10 to the power 6, 10 to the power 6 multiply with this 100, so it becomes the 10 to the power 8. And what's the L? L value is 0.32, so this is a 0.32 is multiplied with the 10 to the power minus 6. Similarly, what's the value of the G? G is what? 1.50 into 10 to the power minus 6, so 1.50 into 10 to the power minus 6 plus J omega C. Omega is replaced by 2 pi f, and what's the value of the C? C is 34.5 multiply with the 10 to the power minus 12, so this is the value of the C. So whenever you calculate this value, so finally the value of the characteristic impedance is, this is 96.2 minus of 0.02 ohm. Again, remember the one thing, what is it? This is the characteristic impedance, and these value is in the ratio of this one. So the value of this characteristic impedance is having a simple unit, that is the ohm, not the ohm per kilometer of the meter. The Z0 is simply calculated in terms of the ohm. Yes, so before move towards the next problem, first of all you have to note down these formulas. What are these? Actually, gamma, as you all know, the gamma is what? That is the propagation constant, and it is equivalent to the alpha plus j beta. So either you have to calculate the gamma, and after calculation of the gamma you are able to calculate the alpha and beta. Or another method is what? You just, gamma is what? Gamma is having the two values. One is, this is what? Mod of gamma, that means it defines the magnitude of the gamma, and psi is what? That is the angle. So here is a formula of calculating the magnitude of the propagation constant in terms of the primary parameter. Similarly, the calculation of the angle that is related to the propagation constant in terms of the primary parameter. Similarly, this is what? This is the characteristic impedance, and this formula is for calculating the characteristic magnitude of the characteristic impedance, and the theta 0 is what? This is the angle related to this characteristic impedance. And what is this R0 and X0? This is the real part of this characteristic impedance, and this is the imaginary part of this characteristic impedance. Similarly, what is the alpha and the beta? This is the alpha is what? This is the attenuation, so this one is the real part of the propagation constant. And what is the beta? This is a phase constant. And what is the phase constant? Phase constant is the imaginary part of this propagation constant. So remember these formulas or note down this one. Yes, so this is the problem second. What happened in this problem? The distributed circuit coefficient of a parallel wire pole mounted telephone line with copper conductor is this, in a diameter space is 12 inches between centers are, these are the primary parameter that is given for this numerical at the frequency of 1000 hertz. So what's the value we have to find out for this numerical is, these are the attenuation, phase velocity and characteristic impedance. So what is the formula? First of all, what you have to calculate here, that is the attenuation. So for calculating the attenuation, first of all you have to calculate the propagation constant. As we have seen already in the previous slide, the formula for calculating the magnitude of propagation constant is what? This is the formula. Actually, formula is what? This one is the r square plus omega, r square plus omega square and L square. So this is the omega. Omega is what? 2 pi and f, and this one is what? This is the value of the L. So r square plus omega square L square and whole bracket of 1/2 plus this one is what? This is the g square. So this is 0.29, this is the g square plus omega squared c. So 2 pi f, this is the omega, and what's the c? This one is the c. So 0.0087, this one is 0.087 multiplied by the 10 to the power minus 6. This one is the 10 to the power minus 6. Okay, whole power in this is the whole power, and this whole term is having the power of 1 by 2. Yes, so the next calculation is for the angle with respect to this propagation constant. Here we have calculated the magnitude, next we calculate the angle. So either you have to calculate the propagation constant with the help of these formulas, or another method is, since we know gamma is equivalent to root of z into y, so from this formula you are also able to calculate the propagation constant. So from this equation, whenever you have to calculate the propagation constant, so this is in terms of the complex form, right? So when differentiate the real when you are compare this gamma with the alpha and j beta, so this real part is equivalent to the attenuation and the imaginary part is equivalent to the beta. So there are two methods, either you have to solve with this formula or with the help of this formula. Now whenever you are able to calculate this magnitude of the propagation constant in the psi, now you are able to calculate this alpha and beta. And what's the next is, this is the velocity. So in this question you have to calculate the attenuation. So this one is the attenuation, that having the unit of dB per mile. And what's the next? Remember the unit, which parameter you have to calculate and what is the unit. Okay, and what the next? This is the phase velocity. So the calculation for the phase velocity is what? This is equivalent to omega by beta. So whenever you have to calculate the beta, then you are able to calculate the phase velocity. So this is in terms of miles per second. Next is what? That is the characteristic impedance. So the characteristic impedance, as we have already calculated in problem 1, so now you are able to calculate the characteristic impedance. So this is the magnitude of the characteristic impedance, and this one is the angle that is related to the characteristic impedance. These two calculations are not asked in this question, but whenever required, so you are also able to calculate the R0 and X0 also. X0 in any numerical. Yes, so now the time for break, so that you can understand this topic very well and do the practice for numerical. In my next lecture, we will move towards the next topic, that is the distortion in transmission line. Thank you.